Hi there. We need to go over some tools in section 2.1 that we're going to need to get through chapter 2 and talk about determinants in chapter 3. So just a couple of things are key. We've talked about inverses of matrices before in class. You guys do need to go back and review that material that we did live before, right? Can't review everything. But just to remind you, so section 2.1 highlights some matrices have inverses. We're talking about multiplicative inverses, right? So some matrices have inverses, some don't. So for example, first of all, what is an inverse again? We say A has an inverse matrix B if and only if AB is equal to the identity matrix and BA is also equal to that same identity matrix. Now you'll notice that what that does, this statement right here, this forces A to be square. Why is that? Well, if it was m by n here, m by n here, if this was n by something else, p, they have to match up, right? Then we would have here something that's m by p. And our identity matrix is square by definition. So it has to be that A is n by n, also so that this can work over here, right? If I had m by n over here and B was still n by p, well, right here we would be forced to have m equal to p. So A is a square matrix if it has an inverse, right? Okay, so let's see, example of a matrix A that is invertible would be one like this. Let's say we had here a 3 here, 0, 0, and a 4 here. So if you think about it, what has to happen right here in order for this to be able to equal the identity matrix? Remember what the identity matrix looks like, right? 1 there, zeros here and here. Well, for that to work, this dotted with that forces this to be a 1/3. Because that's 0, we don't have any restriction here. But this dotted with that, this dotted with that, this then dotted with this, that has to become a 0. So what's here has to be equal to a 0. Same thing with this one. We're going to get 0 times 1/3 plus 4 times something. We want it to add up to 0. Best is to put a 0 there, then this times that, that'll have to be a 4th. So sometimes the inverse matrix looks a lot, very reminiscent of just inverses of numbers. Sometimes. Most times it's more complicated than that. This is actually an example, both of these are diagonal matrices, which are super nice to work with, and that's why you're going to be seeing later in the course, we're going to be striving to make everything act as much as we can like a diagonal matrix. Diagonal matrices commute. So that means that if I have here AB, AB is equal to BA. And you can check it out yourself. If you take these two in reverse order, multiply them, you're still going to get that identity matrices. So matrices, if the two matrices are inverses of each other, they have to commute, right? By definition of inverse. You remember. Most matrices don't. All right, so this is something you had to remember. Something introduced in this section 2.1 that we're going to be using at some key junctures is this property that for any matrices, so if A is m by n, B is n by p, this property holds that their product can be thought of as a matrix whose columns are AB1, AB2, AB, let's see now, how many columns? He's B1, B2, these are the columns of B. So B looks like this. B1, B2, it's got P columns, that's the last one, right? BP. Well, it turns out that any product of two matrices can be thought of as the matrix on the left multiplied by each of the columns. Mind you, most textbooks prove that from the usual definition of matrix multiplication. Our book, and that proof is pretty nasty looking. So our author, David Ley, decided, I'm just going to define it to be this way, that this is matrix multiplication, and not prove anything. Well, in the interest of time, I'm just going to give you a convincing example, not a proof, right? So suppose just an example. Suppose A is our good old 1, 2, 3, 4, and B is 5, 6, 7, 8. So I'm not picking special numbers, I'm just grabbing the first 8, throwing them in there. Okay, so that'll imply that B1 is the first column of that. That looks like 5, 7. And B2 is its second column, 6, 8. Right? What does AB1 look like? 1, 2, 3, 4 multiplied by 5, 7. Right, always checking that that's possible. 2 by 2 by 2 by 1, that'll work. We should get a 2 by 1, right? So this will be 1 times 5 plus 2 times 7. I'm going over this because some people asked me to go back over multiplication of matrices yesterday, April 1st. Possibly an April Fool's joke, but anyway. So let's see, this would be 3 times 5 plus 4 times 7. So 5 plus 14 is 19. What's that? 15 plus 28. Is that 43? Yeah. Okay. What's AB2? Multiplied by B2. B2 is that second column, 6, 8. That gives you 2250. Right, you can do that math. And remember, if you're dealing with a situation where these numbers are a lot nastier, you do have the graphing calculators. You can define one matrix to be one size, another matrix to be another size, and actually just multiply them using the calculator. That won't ever be a whole test question in my class, but sometimes if the numbers are nasty enough, I'll be expecting you to pull out your graphing calculator and do those calculations quickly using it. Okay, again, that's never the whole problem. All right, so for example here, just to demonstrate that AB does look like this, with this is the first column and that is the second column, you could use your graphing calculator. But we can also, because these numbers are nice, just do it ourselves, right? What do we get? well, that times that. Where have I seen that before? 5 plus 14, that's the 19. 1, 2 times 6, 8. Yeah. What is that? 1, 2 times 6, 8. That's 6 plus 16, 22. There's that. And so on. This dotted with that. Excuse the noise. 15 plus 28 is your 43. And this dotted with that. That's going to be your 50, right? 18 plus 32. Yeah, that's the 50. And so sure enough, that's equal to AB1, AB2. Is that convincing? I hope so. I'm not going to be giving you a proof of that, but we're going to be using this clever device in a couple of crucial places in the next video and pretty much throughout the course. We're going to keep coming back to that. Very handy.